Yeah, I'm live on Facebook.
Can you stop sharing for a while? Sure.
It's 11 a.m., the first Sunday of the month, which means we are at Prithvi Theatre. And welcome everybody. Thank you for coming here, those who've come in person and braved it. And thank you all for who are watching online on Zoom, Facebook, or YouTube. Sorry, we have this strange arrangement here with Mayank sitting, because that's the only way he can actually control his computer as well as be seen on Zoom. Usually we love to walk around, but that's not happening today.
Yeah.
But still, welcome to Chai and Why. Thank you all again for coming. This happens on the first Sunday at Prithvi Theatre. The third and fifth Sunday sessions are still online. Once our venue partners, colleges, schools give us the permissions, we will obviously go back to a live session as well, in-person session as well. Just to remind you, a month from today, which will be March 6th, because February has 28 days, we will be back here with another physics talk. Sharonyo is going to talk about the ultimate speed limit and the special theory of relativity. He's going to explain that. So that's going to be a month from now. But for today, we have Mayank Narang, and Mayank is not a stranger to Chai and Why. In fact, I think after me, he's probably given the most Chai and Whys.
I think so.
This is your fourth?
Yeah, fourth.
Yeah, fourth. So Mayank is a astronomer. He's from Delhi, did his bachelor's there, and actually joined TIFR for a integrated PhD. And his PhD work is on how planets form, on exoplanets outside other stars, and he is also has talked about various things at Chai and Why, right from the image of the black hole to how galaxies form, and exoplanets. Yeah, exoplanets, of course, which is his work.
Yes.
And today he's going to tell us about the
James Webb, JWST.
James Webb Space Telescope, this new and fancy thing which is up somewhere. The best part of it is, even as a PhD student, Mayank is a co-investigator on 2 JWST proposals already. And I think that is absolutely non-trivial. So, excellent work. And tell us all about it, Mayank.
Sure.
I'm going to sit there and put some earphones in and see if Zoom audience has questions. Okay, the way we're going to do this, yeah, you can share your screen. The way we're going to do this is we will let Mayank speak. Okay. We will first take a few questions from the Zoom audience, which I will read out so that everybody here also knows. Then we'll stop the live streaming, and we can go and have our chai, and then we can continue with questions. Okay, that way otherwise the Zoom audience will wonder what's happening when we're all having chai. So we'll do that. Okay, so excellent. Let's go ahead.
Okay, thanks Arnab for the delightful introduction, and thanks to the Chai and Why team, everybody at TFR for this perhaps might be the last Chai and Why I gave as a PhD student here, but I like to come back and give a few more. And this is also my first time giving a Chai and Why at Prithvi, so it's a very different feeling. It's a very different kind of a stage, and it's actually a stage. You can see that behind there are some props which maybe the Zoom audience can't see, but the audience that is here can see. So it's my pleasure to talk today. And so today I'll be talking about the James Webb Space Telescope, or it's called now JWST. So the title of my talk is JWST, Unfolding the Mysteries of the Universe. So this word unfolding has a very strong connotation in terms of JWST. And I'll basically try to talk mostly about how this telescope was built, why this telescope was built, and what this telescope is capable of. And since it was just launched a month back, so we don't have any science results from it now. And at some point in the future, I would love to give a Chai and Why on the science results from JWST. But let's not keep you waiting, and let's begin with the talk. So I'll take you back to the year 1995. So DDLJ was playing in the cinema. I was only 2 years old. I was a tiny baby. PV Sindhu was born actually at that year. I always said that PV Sindhu was much younger than me, but it turns out she's just 2 years younger to me. But the most important thing, I think, apart from me being born and being 2 years old, was Hubble taking the deep field image. So what is the Hubble deep field image? So what usually happens in astronomy is that I'll propose for a target that I want to look at this particular star or this particular nebula or this particular galaxy. Never has anybody looked at just blank sky. So even if you look at the sky, since we are in Bombay, we see a very murky sky with only maybe the brightest few tens of stars visible. But if you go to a dark place, let's say 2 hours from now, something like going up on top of Kalsubai and seeing the stars from there you might see a few thousand stars, but there will be patches of sky which you will feel like they are devoid of anything. You point a telescope or even a small binoculars towards that, and you'll see that there are many more stars behind that. But so there are a lot more stars in the galaxy that we can see. So what Hubble did was the Hubble team tried to do was they pointed at a patch of the sky which they thought did not contain many galaxies or many stars, and they just imaged it for like 10 days. So they collected light from 10 days. This patch of sky, you might ask, how big is that patch of sky? So if you take a needle, that is a swing needle, you put it at arm's length, the tip of that needle, the blunt part of the needle, that area, that is the patch of sky that they looked at. And this was the image that they made, if you can see. So you see that this image has many point objects and not many light sources. So interestingly, almost all of these light sources that are seen here, these are actually galaxies with a few stars here and there. And what we see is that there is almost a zoo of galaxies here. We have galaxies which are like spiral kind of things. We have galaxies which are very red in color. Some of them are very blue in color. So we are seeing a snapshot of the universe. And it's actually like a 3D cross section. So what we are seeing is not just the galaxies that are present at today, that is at t is equal to 0, but we are also looking at galaxies which how they were maybe 1 billion years from ago, 10 billion years ago, and the oldest galaxy that we see here is something which is about 12 billion years ago. So this was a first cross section of galaxies or cross section in time that we were able to put out and see how galaxies evolved as a function of time. So this is something similar, like if I take a picture of you, and in the background, you can see your ancestors. And in the background, you can see Shah Jahan. And in the background, you can see a dinosaur. So this is something very similar. So the closest galaxies are very young. The oldest galaxy is being 12 giga years or 12 billion years old. So Hubble, with this deep field image, somehow revolutionized the way science was collected and data was taken, data was published. Because just after this deep field image, they actually made all this data public. And this has more than about, I think, 1,000 citations, this particular image. People have used it for simulations, how to understand how galaxies form, everything. But one of the drawbacks of this image was that we can only see up to 12 billion years ago. So the universe we know is about 13.5 to 13.8 billion years old. So we are missing a large chunk of the universe's history. That is the early history. So, but that's the thing, right? If you want to look at something, you want a bigger and bigger telescope. But that also comes with a limit, because there is something called the cosmological redshift. So as you look further back and back, the light from the galaxies, they turn redder and redder. And as they turn red in color, they become fainter and fainter in the optical wavelengths, and they can only be looked into in the infrared wavelengths. So if you want to look at the oldest galaxies, or perhaps the first galaxies that formed, we need to look into the infrared region. So Hubble worked from UV to infrared, that is from 100 nanometers. So 1 nanometer is about 1,000 times small. 100 nanometers is about 1,000 times smaller than the human hair, to about 1.8 microns. So micron is basically 1,000th of a millimeter. So that is about 100 times thinner than the human hair. So Hubble worked at a very narrow range in the wavelength. But to look at galaxies which are much older than this, we need to go to much longer and longer wavelengths. I'm talking about, let's say, something like 28 microns, 30 microns. So 30 microns is basically 0.3 millimeters. So these are things that you can start seeing with the naked eye. So we are talking about wavelengths of light. If we were able to see, we could see them with the naked eye. So in order to look further away, we needed a telescope to look into the infrared. And in 1996, after the Hubble Deep Field Image, NASA made a committee of 18 members to basically develop a new space telescope to work in the infrared. So this was how the JWST telescope came about. So I have highlighted this major thing, a space telescope working in the infrared. So now let's see why we need to go to space first. So typically when we say we look at something, we look at them in the visible wavelength. that is the rainbow color, that is the VIBGYOR that we see every day. And some of you now must have heard that because of these, like when we came to the theater, there was this infrared temperature gun, right? So you could measure the temperature of objects, or you can measure the infrared light coming from objects using that gun. So these kind of wavelengths are infrared wavelengths, and they are not visible to the human eyes. And they're also not transmissible from the atmosphere. So our atmosphere, as we know, has a mixture of gases. It has the ozone layer. And all of us I'm certain in 4th, 5th standard have learned that the ozone layer protects us from the UV light from the sun. So the atmosphere actually blocks a lot more light coming from all the way from UV to X-ray. The atmosphere blocks. The optical path is where we are allowed to see. The atmosphere is transparent in that wavelength. And that is why perhaps our eyes are also tuned towards that wavelength. There are also certain other atmospheric bands which can allow for some transmission. But if you can see from here, I'm showing basically the amount of light blocked. Can you see my cursor? Yeah, you can see my cursor, right? So the amount of light blocked as a function of wavelengths. And we see that the VIBGYOR line is basically fully transparent. There are some bands in the infrared which can also be observed from Earth. And we regularly do this. And TIFR actually has brilliant facilities to actually observe some of these bands. These are located in beautiful locations like Nainital and Ladakh, which I would like to go someday. But unfortunately, because of COVID, I wasn't able to go. And then we have certain bands longward. But you see, most of the infrared light is actually blocked by the atmosphere. And to actually observe this infrared light, we need to go to space, because there is no atmosphere, so we can observe them and they're not blocked by the Earth's atmosphere. The other important thing is, if you have tried to look at a star with even a small telescope, you see that because of the atmosphere, the sky is very turbulent. Like, this is one of the reasons why stars twinkle. So if you look at a star, because of the atmospheric layers, there is a shimmer to that star. So on a hot day, or maybe if you're close to a bonfire now, since it's winter, if you look at through the like gas rising above the bonfire, you see that the gas is actually turbulent. It's moving like a sap or snake. It's like zigzagging. So because of that, the objects which are behind that gas, they'll also look very wavy and fuzzy. So this is one of the reasons why telescopes based on Earth cannot look at very sharp images. That is because the atmosphere is very turbulent and you cannot actually capture a very stable image. So I'm showing here one such image of a star from a telescope. You can see that how turbulent that image is, how it's pulsating. And this is an image of the moon. You can also see that even though the moon is so close and it's so bright, you can still see that some of the features, for example, this crater, which has a cone kind of thing protruding, that comes in and out of focus. So because of all this atmospheric turbulence, we cannot get any sharper images. So because of the atmosphere blocking infrared light, and because of this turbulence, space telescopes are excellent to observe near infrared and far infrared wavelengths. And then NASA, there have been several space telescopes which have observed in the near infrared and far infrared. There has been the Spitzer Space Telescope, which was the workhorse for the star formation and cosmology community till about 2019, when it was retired. There has also been the Hubble Space Telescope, which is again a telescope that worked at much longer wavelengths. We're talking about something like 100 microns, which is actually 0.3 millimeters. So that is like huge when it comes to it. So there are many telescopes which NASA has launched into NASA and ESO, the European Space Satellite, both have launched that have worked in the infrared and far infrared regime. So NASA has a huge legacy of building such instruments along with ESO. So one of the instruments they wanted to build was called the James Webb Space Telescope. So James Webb Space Telescope, or JWST, is a 6.5 meter telescope. It is the largest telescope that has ever been flown. So it operates from 0.6 microns, that is 6,000 nanometers, that is the red color of light. So if you look at red, that is around 6,000 angstroms, to 28.5 microns, which is basically something like 1/330th of the human hair. So it works at a very long wavelength. It covers from optical to mid-infrared. It's also a very cold telescope, so operating at -233 Celsius. So you can imagine how cold it is at -233. Like Bombay people, they get cold at 15 degrees Celsius. Delhi people, they get cold at maybe 2-3 degrees Celsius. But -233 is like very, very cold. And it's operating at a specific location in space called L2. And I'll come to why it was chosen at L2 and what L2 is in the later part of this talk. So now let's look at, so these are the main reasons why we need a JWST kind of telescope. So let's first look at the mirror itself. So the JWST mirror, as I said, is a 6.5 meter mirror. It's very large. So this is a person Hubble was 2.4 meters long, while JWST is 6.5 meters long. So you can imagine, like, I am about a meter and close to a meter and a half. So it's like me standing head to toe on top of each other. That is a huge mirror. And that would be like amazing if you can build it as a single thing. But as you will see, it's made in as a segments. Hubble was only 2.4 meters. So we can actually calculate the amount of light JWST collects versus the amount of light Hubble collects. So the amount of light collected by telescope is basically the square of the radius of the telescope. Or so because Hubble is about 2.5 times smaller than JWST. So JWST collects 6.5 times more light than Hubble. But Hubble only worked from 1000 nanometers to 1.8 microns. Hubble works from 600 nanometers to 28.5 microns. So JWST has a much larger wavelength range, which Hubble never had access to. So in this regard, people claim, or it has been shown, that JWST is about 100 times better than Hubble when it comes to imaging. And I'll show you some sample images to confirm this. So as I was saying, I'll show you some sample images. So I don't know whether you can see this, but you can see this is a Hubble image. You can see a very blurry, you can't really make out what this is. So if the same target was taken up with JWST, so in the center you see there is some bright spot. That bright spot is actually a quasar. So these are some of the most energetic objects in the galaxy, not in the galaxy, in the universe. And you can clearly see that with JWST, we'll be able to look at not just the central engine, which is driving the brightness of the galaxy, but also the material around it. So with the large collecting area that the mirror has, it can look at fainter objects, and it also has a better angular resolution, because even the angular resolution is dependent on the size of the telescope, and the angular resolution, basically it's proportional to the diameter of the telescope. And again, the diameter is 2.5 times better. So you see the light collecting area is 6.5 times more. The diameter is 2.5 times more. So that's already a factor of about 6.5 into 2.5. You can do the mathematics. I'm not great at mathematics. I'm an observer, but that's about factor 15 better. So, but the detectors are also much better in the JWST, because we have now. So Hubble was launched 30 years ago. 30 years ago, none of us had cameras in our cell phones. But the cameras that we have now in our cell phone, they are actually a legacy of the work that was developed for Hubble and other space telescopes. So we can say that at some point, if somebody asks us, what has astronomy given us? I can always say it has at least given me a selfie camera. So with the improvement in detector physics, Hubble now is at least 100 times better. So JWST is at least 100 times better than Hubble, if not more. But as I'll say that the wavelength coverage that Hubble has and JWST are very different. JWST and Hubble are complementary to each other, but I won't call JWST a successor to Hubble. Maybe a successor to Spitzer, but again, JWST has a much wider coverage. So it's a combination of successor. I would say it's both successor to Hubble and Spitzer Space Telescope. So as I was saying that JWST is a 6.5 meter mirror. So these are not actually, it's not a monolithic mirror that is a single mirror. It's actually made out of very different segments. So Hubble was a monolithic 2.5 meter mirror, whereas JWST is actually segmented into 18 such segments. Each of them are, you can see they're yellow in color. So there are 18 hexagonal segments of 3.2 meters each. So 3.2 meters is about 4 feet. So that's like this big of a mirror. They're coated with beryllium. So beryllium is something that we don't really talk much about. It's only when we discuss periodic table and when we do that periodic table song, that hydrogen, helium, lithium, beryllium. So that's when beryllium comes. We haven't made it, like lithium batteries people have talked about, helium people have talked about, sodium everybody knows, NaCl, namak, salt. So sodium and chloride. Beryllium is not peculiarly important to science, at least that is what I thought, but it turns out it's very important for building mirrors, especially space mirrors. So all of you must have at some point, especially us kids, they would have heated a spoon. And sometimes what happens, let's say you're heating some glass and there are 2 glasses stuck. So what happens is your mom will tell you that put it over the flames and it will heat up and it will open up. So why does that happen? So when you heat up a metal, it actually expands. And when you contract and when you cool down a metal, it actually contracts. So that is why sometimes we heat them over and they expand so we can remove those glasses. But beryllium has a very peculiar property that below 100 Kelvin, that is below about minus 173 Celsius, it does not contract. So it will maintain its shape. So even if we can cool down the mirrors to about 100 Kelvin, then the mirrors won't, then any fluctuation in the temperature, the mirrors won't change its size below 100 Kelvin. So which is very important because we are building a telescope. We want the mirror to be as flat and as perfect as possible. So that is why when JWST was launched, the mirrors were initially slightly bigger than what they are finally planned to be. So when it goes and cools down, it will actually become a proper hexagonal mirror of about 32 meters, and which will take up a proper shape. You also see that the mirrors actually are coated with gold. So there is a golden color. So it's not just a paint job to make it look pretty. It's actually gold. And there is a very important reason why it's colored with gold. It's golden in color and not, let's say, silver or gray. So most Earth-based telescopes or optical telescopes which have mirrors, they are basically coated either in aluminum or in silver. Both of aluminum and silver are very good reflectors in the optical wavelength, whereas gold is a very good reflector in the infrared. So there is a micron thin layer of gold on JWST. The total amount of gold used on JWST is only 50 grams. I'm certain most Indian women have more gold in their tijoris or in their safes than 50 grams. So it was a micron thin layer of gold which was placed on this telescope. But this micron thick layer is enough to actually reflect 99% of the infrared light which is falling on this telescope. So that is why this mirror is gold coated. So I've talked about why the mirror is gold coated, why the mirror is made of beryllium. Then the next question is, why was the mirror segmented? So we could have launched a single monolithic mirror. It's just 6.5 meters. We can do such things. But there was a legacy or a learning program, or there was a legacy behind this as well. So when Hubble was launched, there was a problem with its mirror. So they had made a very polished, accurately mirror, but what happened was that somebody did some miscalculation, and the mirror was precisely polished, but it was off by a few millimeters. So can you imagine being off by a few millimeters, and it was then producing such blurry images? If you can see this image, is the image of a galaxy. Then it was not properly polished, and it was producing a very blurry image. So then astronauts had to go into space and repair it. But since Hubble was only orbiting about 200 kilometers away, we had the NASA shuttle program. So astronauts actually had to go open the telescope, remove some components, put up another component which could compensate for this properly polished but inaccurate polish of the mirror. And they were able to make such blurry images into these kind of pristine, beautiful images. So Hubble then has been regularly updated, and now it's most likely on its last legs. But with JWST, we won't be able to do it because it's being launched at an orbit which is very far away from Earth, and also NASA does not have the shuttle program anymore. So there is no program, or there's no contingency in place where we can go and repair the telescope if something goes wrong. So if we have segmented mirrors, we can actually move these mirrors and adjust it to actually make a proper image. So JWST, each of these hexagonal segments has actually actuators on its back. So we can actually make the telescope make each of the segments independently tip and tilt. They can also bend forward and backwards, and they can also be pushed inward or outward. So the curvature of the telescope can also be changed. So with this, we are actually able to fine tune the image. And the way the JWST team designed the instrument was, on Earth, they'll actually just place the mirrors and roughly align them, and then they'll send it to space. And once the telescope is in space, the mirrors can actually move. And these mirrors can be finely tuned, and they can be moved a few nanometers to few millimeters in length. And with each step, as has been written there, being a 1/10,000th of the human hair. So that's about few nanometers in precision. So you can basically move each of the individual telescope segments. And why it's needed to move each of these individual segments, so that we can make a very perfect image. So this is how JWST will spend the first almost 90 days. It will observe some bright targets, maybe a bright star. And then the light will come, and what will happen is that since the telescope is not properly aligned, we'll get 18 images of the star on the telescope field of view. So this is the telescope's focal field of view, and we'll get 18 such images. And then each of the mirrors, as you can see here, are being micro adjusted such that we can combine all of them into a central location. And this will continue for almost 90 days. that is the commissioning time, where they'll be actually finally adjusting each of these mirror segments so that we can create a very crisp and a perfect image. And you can see that as the mirrors are being aligned, the 18 images actually fall onto the center. So this was one of the major thinking behind creating a segmented telescope and not a monolithic single mirror. The other thing was there are no telescopes which are large enough to actually launch something which is 6.5 meters. So even the best telescope, which was the Ariane 5 rocket, which has been developed by ESO, that can only house something up to about 5 meters. And here we are talking about just a 6.5 meter mirror of the telescope. So the mirror had then been segmented, and there were 2 into 3, that is 6 segments which could be folded. So I told you, right, this word unfolding the mystery has a mysterious origin in the title. This is one of the mysteries, that the telescope can actually be folded in and out. So it can actually be folded like an origami, or it can be folded like this, so that you can have a very narrow cross section of the telescope, which could be placed into the rocket. And the telescope can also be obviously independently moved in the XY directions, so that there is no misalignments. So here I'm showing how the telescope will actually unfold or the mirrors will actually unfold. So each of these, the side 6 mirrors, side 3 mirrors, they'll actually fold inwards to create a single monolithic 6.5 meter diameter telescope. So we have seen now why it was sent to space. That is because we want to avoid the turbulence in the Earth's atmosphere, and infrared lights are blocked because of the Earth's atmosphere. That is why we send it to space. We have seen now why it's gold-coated mirrors, because gold is the best reflector. Why beryllium? Because beryllium does not contract below 100 Kelvin. And now we have also seen why the telescope was segmented. So we have answered at least 2 of these questions. At least the first question we have answered about the mirrors of the telescope. Now let's look into the second and third question. So the wavelength coverage of the telescope is from, as I said, 0.6 microns to 28 microns. And there are many instruments on JWST which will be complementing each other and observing at various different wavelengths. I'll actually come to these wavelengths or these instruments in a later slide. But just to make it clear that JWST is a very large coverage from the reddish color, that is at 0.6 microns, all the way to mid-infrared. And to do that, and to actually observe these lines, we need to keep the telescope very cold, and also at a very specific location in space, such that we can actually keep the telescope very cold passively. So let me ask you a question. Do we all emit light? We reflect light, that is true, but we also emit light. So when all of you came to this Prithvi theater, all of you had your temperature checked, right, with the thermometer gun. So that thermometer gun actually checks out or measures the amount of light or infrared light which is being emitted by the body. So all of us human beings are actually emitting infrared light. So if you look at all these infrared cameras, they're just picking out the light that we are emitting. So that at a human which is healthy, let's say, has a temperature of 35 Celsius, not Kelvin, then that means that human is basically frozen. But a 35 Celsius human, that emits at 10 microns in wavelength.
Just give the online public a few minutes to type, a few seconds to type their answers. Everybody said yes, yes, yes.
Okay. Good. It's good that the online public is also listening.
Yeah. They're listening and they're active and they're commenting, and we have 86 people on Zoom and another 50 plus people on YouTube who are asking questions, and I'm like just trying my best.
Yeah, we'll answer them. Definitely, I'll try to answer all.
I'm answering the ones I know. Yeah. Okay. Keep going.
So as I was saying that at 35 Celsius, we are emitting at 10 microns. So if I have to observe something at 10 microns, I don't want a human being in front of me, because I'll be blasting out radiation like it's something like DBZ or Dragon Ball Z. I'll be like covered in radiation, and everybody will be like, everything will be blinded by that. So we need to keep the telescope away from human beings. Even the Earth, as we know, let's say we are sitting in a 30, because Mumbai, it's 30 Celsius is very common. That's again 10 microns. So even keeping the telescope on Earth away from human beings will not be an answer. So
is micron the same as micrometers?
Yes, micron is the same as micrometers.
And what is a micron?
So micron is basically, if you take a human hair, a micron is basically 100 times smaller than the human hair, or if you have basically 100 times smaller than the human hair. And if you have good thick hair, maybe 70 times smaller. And if you have weak hair like me, maybe 1,000 times smaller.
About 100 times.
Yeah.
Good.
Okay. So even Earth, as I said, is a huge source of infrared radiation. And since we want to observe light coming from objects which are, let's say, 28 microns. So 28 microns means minus 170 Celsius, or minus almost 270 Celsius, or minus almost 200, maybe 100 Kelvin. So we need 35 Kelvin. So we need to go very far away from Earth and very far away from human beings to avoid this infrared light. So that is why this telescope was launched in space, to keep us Earthlings away from it, the radiation from us away from it. So we need to cool down the telescope. So as I said, both Earth is definitely an infrared source. Even moon emits infrared. Sun definitely is an infrared source. If you go out on a hot day, I'm certain you will feel the heat. Even if you're not directly in the sun, you will still feel the ambient heat. So we need to avoid pointing the telescope at these objects. Furthermore, the telescope and the instrument both need to be cooled down, because these are detectors, and these are very sensitive detectors. So as the temperature rises, the sensitivity of these detectors goes down. So we need to keep these telescopes also very cold, and these instruments very cold. So the average temperature in the space is about 2.7 Kelvin. So if we launch the telescope in space, it should at some point go down to 2.7 Kelvin. But because of the sun's glare, this might actually heat up the telescope as well. So we want to stop or avoid the sun's glare as well. So how do we do this? So the first thing that we do is we place the telescope at a very specific location. So we can't place the telescope around Earth, because we will be getting constantly the background radiation from Earth. Because if something is orbiting Earth, then what will happen is that even if your telescope is pointed away from this, you will be still getting radiation reflected off from Earth, and that will cause the telescope to heat up. So we put the telescope away from Earth. So where do we put a telescope? Because if we put something in space, it will actually orbit Earth. It will orbit the Earth, Moon, Sun system. And what will happen is that it can come in and out between Earth and Moon, Earth and Sun. So it can cause lots of havoc. It can also actually heat up the telescope, which will basically ruin our instruments. So we need to put it in a point in space where it does not move. And if you solve the gravity, so all of us have at some point learned about gravity, right? That if you drop an apple, it fell on Newton's head, and Newton said that gravity. But so if you have two bodies, then you can attract each other because of the gravitational force. So in a 3-body system, that attraction becomes very complicated. So it's like a Hindi love triangle. I love you, you love me, both of them also love each other. So it's a very complicated interaction. So but the outcome of such complicated interactions is that there are stable points in space, which are called Lagrange points. So this was done by a French mathematician called Lagrange, because all physics notations have some French mathematician or German mathematician like Gauss, Euler. So it's always Lagrangian. Okay, Euler. Okay, we have some mathematicians in the top who get very pisky. It's Euler or Euler. But yeah, we have stable points in space where if you place an object, it will not move. And there are 5 such stable points. They're called Lagrangian points. So we are basically going to focus on L2 and L1. So L1 is called the first Lagrange point. It's between the Earth. It's between Earth and the Sun. So it's an orbit which will always point towards the Sun. And the upcoming ISRO mission called Aditya L1, the name says L1. So that will be placed at L1, where it will be constantly monitoring the Sun. So many of the solar missions that NASA has launched, they are also at L1, and they are completely always looking at the Sun. There's one more position called L3, which is behind the Earth-Sun line. So it's on the opposite side. So this is not usually preferred because, first of all, it's very far. And then because of the Sun, how will you communicate with the Earth? So we need to place an object which is significantly far away from the Sun, but also close enough, significantly far away from Earth and the Sun, at a stable orbit, but also such that we can communicate directly. So that actually orbit is called the L2 orbit, or the L2 Lagrange point. So again, on the Sun, Moon, Earth system, this is towards the other end. So this is again a stable point. If you place an object in the L2, it will keep on rotating around the L2.
Okay. Just looking at questions, I think L2 is confusing and Lagrange points is confusing everybody. So may I request you to just go through this Lagrange points one more time slowly.
Sure.
We have people in the 5th standard, 7th standard, etc. So just let's give them an idea of what this is.
Okay. So
and I'm sure here everybody is also not so clear of the Lagrange point. Yes. See? Hey, by the way, you guys can put your hands up and ask.
Yeah, you can ask questions as
We're
well.
always allowed to
Yeah.
do that.
So, okay, let me then again explain Lagrange.
We've got more than 100 people who are all asking away, and there's no way I can keep up with.
So let me again explain Lagrange points. So
yeah, this Lagrange points one more.
Yeah. So imagine, so if you have the Earth and the Sun, the Earth is going around the Sun, right? So now, if you have another third body, let's say the Moon, or in our case, our telescope, what will happen is that the telescope will go around the Earth, which is going around the Sun. So the telescope will also indirectly go around the Sun. And because of the complex gravitational forces that might be acting on them, the telescope can actually spiral inward or outward. But there are certain points in space where if you keep a third object which is orbiting Earth and which is both orbiting simultaneously the Earth and the Moon, that third object can be placed at a particular location in space such that it can actually easily orbit all of these two bodies without falling inward or outward. So these such stable points, or points where you can keep an object and it will always be there and not move here or there, are called Lagrange points. And there are 5 such Lagrange points, and we'll basically be focusing on Lagrange point number 1 and 2. So Lagrange point 1 is is between Earth and the Sun. It's on the sunward side, and if you place an object here, it would always keep on observing the Sun. The second Lagrange point, or L2, which is basically what we want to place a telescope at, is away from the Earth, and it's on the again on the Earth Sun-Earth line, but towards the other side. So these are the Lagrange points. So these are stable points in space where if you keep a telescope or if you keep a satellite, it will always be orbiting that particular. It will always remain in that position, and you don't have to fire up rockets and thrusters to actually keep it at that position. Whereas if you keep a telescope somewhere here, that is some arbitrary position, then you have to keep on firing thrusters and you have to keep on adjusting its orbit or trajectory to keep it in the same place. Whereas L2, that is the Lagrange 2 point, is a stable point where you can keep it and it will remain there without expending much fuel. Huh? Yeah, I was coming to that. Yeah. So
again, the question. Please repeat the question, because otherwise
so the question was, is the L2 point beyond the orbit of the Moon? You can yes, it's beyond the orbit of the Moon. So you can clearly see from this figure also that if this is the orbit of the Moon, the L2 point is here. So so the orbit of the Moon is something like 300,000 kilometers. That is 3 lakh kilometers.
There's a question which is a very nice thing. Mm-hmm. Suppose there are 2 people, mm-hmm. and they were playing 2D. Mm-hmm. Right? Yeah. The point at which they are holding hands, that is stable. That is stable, but that is a center of mass. If you can't orbit that point. Okay. Yeah. So it's slightly different. Yes. It's not like that. Yes. All right. Okay. So as I was saying, that this L2 point, so the telescope has to be placed at a position where it does not look at the Sun. So that removes L1. L3 also removes because it's again looking at the Sun. It's far away from Earth. L4 and 5. Again, they can be either looking at the Sun or the Earth. So L2 is the only point which avoids looking at the Sun because the Earth prevents it from looking at the Sun. So you're blocking most of the sunlight, not all, but some of the sunlight. And it's actually quite far away from Earth. So the Moon is something like 300,000 kilometers away from the Earth. That is 3 lakh kilometers. Whereas L2 is about 1.5 million kilometers, or that is 15 lakh kilometers away. So it's almost 4.5 times farther, or 4 to 4.5 times farther away from the Earth Moon system. So it's quite far away. So as you're very far away from the Earth, so as you know that if you look at an object which is farther away, it will appear smaller and smaller to our apparent vision. So it's far enough away that using a single sun shield, we'll be able to block most of the light from the Sun, Earth, and the Moon system. But it's also close enough that we can, using very little rocket fuel, we can send up a telescope there. It's also close enough that if we place a telescope much farther away, then communication becomes a problem. So it's close enough that we can actually communicate with it using the Deep Space Network. So the Deep Space Network is a NASA network of giant radio telescopes or radio dishes. So these can be as large as 100 meters. They're constantly monitoring data from all the NASA telescopes. So there are several of these deep space dishes. Some of them are in US, some of them are in Madrid, some of them that is Spain, Europe, Spain, some of them are in South Africa, some of them in Australia. So they are basically covering the entire globe such that at any time there is at least one telescope, a radio telescope or radio dish which is pointing at a NASA telescope.
So you need to be close enough that you can communicate with the deep space network. So the L2 point was chosen. It was also chosen because it's a stable orbit and it's away from the sun-moon system, sun-earth system, and you can block most of the sun's light due to the earth itself. However, still the earth is still bright enough in infrared. Also, the sun it's not a complete blocking, because if it was completely blocked, then we won't have any solar power at the telescopes, because again, these telescopes are powered by the sun. So we need to have a very complicated system of somehow dissipating the energy or removing the energy or reflecting the energy which is coming from the sun. For this, NASA developed a very ingenious method, which is called the sun shield. So basically, imagine like if you have played tennis or basketball. So imagine that huge kind of a sheet of reflective material, which can actually block most of the light from the sun. So it's a tennis court sized sun shield. And these are not just one sun shield, these are actually 5 layers. So basically that old Lagan song, Pancho mil jaye to ban jaye mutti type. So you have basically the power of 5 shields, which can protect the telescope from the sun's light. So you can see that these are basically human beings. You can see there. So compared to them, the sun shield is so large. There are also 5 of these. And each of these is basically going to be folded up when it's launched in the telescope. So here they're unfolding the sun shield, or basically they're packed when they folded them. So they're right now unfolding it to see how it will perform in space. So these are 5 layers which all need to be unfolded. And one of the delays that was caused when JWST was first launched was because one of this sun shield actually got a tear, or it ripped. So imagine if this happens in space, then the telescope is gayo. It's gone. So what happened? So what they did was they almost spent like the next 2-3 years perfecting how the sun shield would be open and closed. So as you can see that the sun shield has a very silver kind of color. So let's look at why that is. So the sun shield is actually made of something called krypton. So anybody who's working on electronics or in condensed matter will know what krypton is. So krypton is like a very thin polymer kind of, it's basically at some point given us tapes in our labs. So it's a very yellow thin polymer. So with this krypton layer is actually 0.025 millimeters. So if you have that scale that we use in school, so you have 1 millimeter points marked in that. So imagine 0.025 times that 1 millimeter. So again, if you take a human hair is maybe few points, few microns. So these are again 10 times smaller than the human hair. So these are very thin layers, and they're coated with aluminium and doped silicate. So the bottom 2 layers, these are called layer 1 and 2, which will be looking at the sun directly. So they are coated with something called doped silicate. So doped silicate is a very good infrared reflector. So basically what will happen is that all the light which is coming from the sun, it will get reflected back into space. And these layers are only few 100 nanometers to 50 nanometers in length. So again, these are very, very thin, the coating of doped aluminium and silicate. So it's very interesting that we are able to build something, fold it and launch it to space, which is so thin. Imagine how thin, like it's 1/50th or 1/100th of the size of a human hair. So we are actually launching something this fragile and this thing into space. And as I said that there's going to be 5 layers. The first layer is going to be at 85 Celsius. So that's very, very hot. So it will be directly looking at the sun. The 5th layer, which will be the final layer, it will be at minus 233 Kelvin, sorry, 233 Celsius. So there's a minus sign here. So it will be very, very cold. So it's between these 5 layers that we have almost a gradient of 300 Celsius. And most of the energy between these two will be dissipated in that. So imagine one end of the telescope is at 85 Celsius, one end of them is minus 233. So imagine how much energy has been blocked just by these 5 thin sun shields. These are basically micron size, 50.025 millimeters. So imagine how good of a reflector and how good of a design this is, that you're able to reflect almost 300 Celsius of energy from the sun. No, there is going to be a solar, as I said, that you can't have this. So the question is, how is this telescope powered? So this telescope is going to be powered by the sun. So there are going to be solar panels. And an advantage of L2 is that you will have constant sun. So what will happen is that since it's orbiting both the Earth and the sun simultaneously, there will always be some amount of sunlight which will come to the telescope. So what will happen is, so imagine if I have the perfect example. So imagine if I were this is the sunlight coming. So what I can do is I can block most of them, but still you can see that there is enough light coming from around my hands. So this similar thing will happen. So the Earth will block most of the sunlight, but there will still be enough sunlight to power the telescope. And even that minuscule amount of sunlight is still able to heat the telescope up to 85 Celsius. So it will be powered by the sun, but we don't want it to be too much powered by the sun that the telescope heats up. So that's why we'll have these layers as well. And these layers will be folded when the telescope is launched. These layers will be folded, and as the telescope gets commissioned, these layers will open up. And I'll show you an animation of how these layers will open up and how the telescope will finally unfold. So this is the second mystery of being called the second reason why this talk was called Unfolding the Mysteries. It's again the sun shield which was folded up and which will be unfolded to basically protect the telescope from the sun. And that is the second reason why I called the talk Unfolding the Mysteries of the Universe. So as I was saying that this will be basically blocking the sun. So there was this very cute cartoon on XKCD. So half of people who work in science would know this. XKCD, it's a comic writer that writes about our daily lives as students and as physicists and as mathematicians, as biologists, as basically anybody who's doing science. So the joke goes that the reason why JWST put up the sun shield was to actually protect the Earth and the sun from the telescope's powerful flashlight. So it's a camera, right? So it's attack. There's a flashlight. So the reason why it was put in is because we don't want the glare to come from the telescope. But that's a good pun, but actually it's the opposite. We don't want the glare from the sun coming and hitting the telescope. But because of this sun shield, we are able to actually cool down the telescope to minus 233 Celsius. So this is called passive cooling. So what will happen is that as the sunlight hits the telescope, most of the sunlight will be reflected back. So if you can see, so this is the sunlight, it will hit the first layer of the sun shield. Most of it will be reflected back to the space. But because it's a normal thing that some amount of light will be absorbed, some amount of heat would be absorbed by the sun shield. So what will happen is that the first layer will absorb some heat from the sun and it will reflect it and radiate it. So what will happen is part of the light will go upwards and it will hit the second layer of the sun shield. Then the second layer will actually heat up and most of it will be reflected back. But some of it will be heating up the second layer, which will heat it up. And again, it will emit in infrared towards the first third layer, which will again reflect it, heat it, reflect it, and so on and henceforth. So what will happen is that most of the light which is being sent by the telescope will actually be, by the time we come to the fourth layer, will already been dissipated. And the way that the sun shields are designed is that the bottom layer is the longest, then it's a smaller and smaller and smaller. So it's like a pyramidal kind of thing. So that is because then you can actually have the energy being trapped between two of the sun sheet layers. They can actually reflect out and zigzag and be emitted out. So this is like an ingenious design because you're not just by putting up a mirror or basically a shiny reflective surface, you're able to block 300 Celsius of sun's light or 300 Kelvin of light or whatever units you want to take it in. So, and this is one of the reasons why we did not have a single layer. We had multiple layers, because if it was a single layer, then the bottom layer would get heated up and then energy would have transported through that layer towards the telescope. That would also have made the telescope very heavy, because imagine having a single layer of aluminium or something, which is like almost 3-4 feet in thickness. So that is why they made multiple layers. And also because between these layers, there is nothing. There is vacuum of space. Vacuum is an excellent insulator. It's only the heat which is being radiated away as light or infrared radiation that will pass through. So that is why it was also decided that we'll make it into multiple layers. So with this,
how do they decide the precise number of layers? It has to be 5 or 4.
So the question is, how do they decide the precise number of layers? So a lot of work goes into this thermal structure and thermal stress test. So in principle, JWST would work perfectly fine with 4 layers. The 5th layer is added just for protection. So imagine that because it's a telescope in space, there might be meteorites, there might be some small dust fragments. So what can happen is that these small dust fragments can actually pierce this sun shield, and part of it can be torn away. So you have one more extra protection by the 5th layer. So by 4th layer, most of the energy has been dissipated, and the 5th layer is mostly for let's say, as a contingency. Again, it's a very interesting concept that the way these layers are actually made, so it's not a single sheet of Kapton. There are actually runners and chasers in these layers, which can actually be, which are actually sort of sewn in or fused in. So even if it gets torn out at one place, the tear does not spread to the entire sun shield. So a part of the sun shield might get torn off, but the other parts will still function. So a lot of structural material science and structural engineering has gone into this. A lot of thermal engineering has gone into designing these 5 layers. Even the way the layers are so it's not a flat layer. These are actually slightly curved inwards. So it's mostly like Anjali, if you call it. So that the maximum distance is where the telescope is being is sitting, and then the distance progressively decreases. The distance between each of the layers progressively decreases, but it's still enough that we can still reflect most of the light and most of the infrared and block the sun's glare. Yeah. So now we have discussed why it was placed in L2 and why we have a sun shield. So what can happen is now, because of the sun shield, we are able to get down a telescope to work at 37 Kelvin. So which is very, very good. But what happens is that we want to see light which is much farther away. So we want to see much light which is much redder, so much more in the near infrared and far infrared. So as I said, that a 35 degree human being emits at 10 microns. So if my telescope is at 37 Kelvin, if my telescope is at 37 Kelvin, it will be emitting at 3 microns. So that's still a lot of energy being deposited to the telescope. So what we need to do is we need to cool down the telescope further. And ideally, to work at 28 microns, you need at 28 microns, the radiation that is being emitted by, let's say, a body is about 35. So a body which is at 35 Kelvin emits radiation at 28 microns. So we need to go down to significantly lower temperatures to remove the background. So in JWST, as I was saying, there are 4 instruments. 3 of these instruments work between 0.6 microns to 5 microns. And then there is one instrument that works from 5 microns to 28 microns, so which is called MIRI. So this MIRI instrument needs to be cooled down further. And for that, there is something called a cryocooler, which can take the telescope down to an operating or at least the MIRI instrument down to an operating temperature of less than 7 Kelvin. So we are just 7 Kelvin above the absolute zero temperature, and only about 4.5 Kelvin above the minimum temperature in the universe. So we are operating at a very, very cold or very, very cool temperature. So this is why, in combination with the sun shield, the JWST also has a cooler on it. We can discuss that if you want at a later point. But now we have discussed why JWST was launched, where it's going to be launched. We have also discussed about the mirrors, how they were made, what they were made of. We have also discussed why it needs to be cooled down. So now let's look into the JWST instruments. So as I was saying, JWST has 4 instruments. It's called the NearInfrared Camera, NearInfrared Imager and slit spectrograph, NearInfrared spectrograph. So you see that the 3 of the instruments in JWST are called near-infrared instruments, and they did not come up with any fancy names. NearInfrared Camera. You could have given some acronym. Like there are such beautiful acronyms like Espresso, Carmenas. Carmenas is a red flower. Espresso, everybody in institutes drinks. So these are like. Then there is Lucifer. Have a nice name. What is the NearInfrared Camera? NearInfrared spectrograph. I'm like, these are like sentences, like descriptions, not instrument names. But anyways, these are the instrument names. So let's look at these 4 instruments one by one. So NearInfrared Camera, or NIRCam. So at least it has a nice acronym, NIRCam. So it's the primary imager for JWST. So this will be the primary camera that JWST will be using. So it operates from 0.6 microns, that is 600 nanometers. That is the red color of wavelength of light, all the way to 5 microns, which is basically all the near infrared wavelengths. So this is going to be also the first instrument that will be commissioned for JWST. So this will be the first. This is the first instrument that has now been started cooling down, and people are now trying to commission this instrument. So this will also be the instrument that will help us actually align the mirrors. So as I had shown in a previous slide, let me go down way back. So that each of these mirror segments will be moved right individually. So it is going to be because of this particular camera that will be staring at it. So this is called NIRCam. So most of the JWST, so this is the slide. So So you see that this adjustment will be based on the NearCam imaging. So NearCam will be used to basically adjust these actuators. So this is going to be the first instrument that will be commissioned. It's also the workhorse instrument for JWST, and a lot of proposals on JWST, or a lot of telescope time on JWST is actually given to this particular instrument, which is called NearCam. So NearCam is a very interesting instrument because it has it can also give you something called spectra. So images, everybody knows that you click a photo, that's an image. So what is a spectra? So if any of you have looked at a prism or even a rainbow, so you see that the white light from the sun actually gets dispersed into several colors. So that is a spectra. So what NearCam has is also called a spectrograph, which can actually convert the broadband light or all the infrared light which is coming into several, it can actually disperse it into several colors or wavelengths. And we can actually study the composition of many different things, many different stars, just by looking at how the light gets dispersed in the spectra. This NearCam also has something very interesting that's called a coronagraph. So if you see this slide here, or this movie here, so this is a movie of a exoplanet. So this is the central star. So what happens is that NearCam has a coronagraph. So what it can do is it can actually come and block the central light from the star, or it can actually block the light from the star. And what can happen is that if you block the light from the star, because the star is so many times brighter than the planet which is orbiting it, you can't see the telescope, the planet when the star is visible. So it's like if you're looking at a lighthouse, if you're looking at a firefly or a Juhu, and you look at it close to a lighthouse, because of the lighthouse, you won't be able to see the Juhu or firefly. But the moment you switch off the lighthouse light or the light from the lighthouse, you will be able to see that firefly. So the same thing is happening, or the same principle is being used. We are using very complicated optical setup. We are able to block the central light from the star. And because of this, we are able to see the faint planet which is around this. So let me just play the movie once more. So you block the central light and you can start seeing the planet which is around it. So this is called a coronagraph, and NearCam will have a coronagraph which will be used to detect exoplanets. So exoplanets are planets which are outside our solar system and they are orbiting other stars. So NearCam will actually be used to detect some of these exoplanets and to image them, and that is get their photographs. So the question is the blocking is it a physical blockage or is it some other thing? So it's actually a complicated setup where they're actually using something called diffraction of light to actually block the central light. It's basically disruptive interference. So what will happen is that they'll have something which will diffract the light such that the light from the central region does not come. You might ask, what is diffraction? So if you have taken a small hair, put it in front of a laser light, or if you look at the door, if you are at a very dark, if it's very dark in your room, you slightly shut down, you almost close the door, but there is a slight sliver of light still coming. You'll see that slight sliver of light gets bent. That is basically an example of diffraction. So in this telescope, it's a combination of diffraction and masks, which will be used to block the central star. The next instrument is called, again, it's a NearInfrared Imager. So JWST has a love for near-infrared things. It's called a NearInfrared Imager and Slitless Spectrograph. That's a mouthful of, it's a huge title. It's called NIRSIS. Again, this will work from 0.8 microns. So this is barely at the wavelength range where the human eyes can work, but your mobile camera can actually pick up 0.8 microns. So if you ever take your mobile camera and look at it, look at a cell phone room, you take your mobile camera and look at a TV remote, you will see that even though and press on some buttons, even though you can't see any light coming from the remote, your cell phone camera will be able to pick out that light. So anybody who has a cell phone camera, and after this talk, you can go point it at your TV remote, take a video and see, you'll be able to see the flash of light coming from the bulb on top, or the bulb on top of the remote, which you can't see with the naked eye, but because of the infrared, because these cameras also have some amount of infrared sensing capabilities, you'll be able to detect them. So this is like the homework for all of you. Go out, check out, and see if you can detect the light coming from the TV remote. So as I was saying, this is another infrared instrument, NIRSIS, and this will be operating from 0.8 to 5.5 to 5 microns. This is again a camera with a spectrograph. So as I was saying, that spectrographs are basically, you can disperse the light into its various different constituent components and see how that light looks. So, but this is going to be something very interesting. So typically what you have to do, and there is also a small kid with a prism in his t-shirt. So that is basically an example of spectra. So if you can see, maybe later you can see. So this spectra, so what will happen is that you typically need to put the light source and you need to have a very narrow slit so that you can only look at the light source. So it's something like this, a narrow slit. So that's called a slit spectroscopy. So what happens if you remove that slit? You can actually get spectra for a lot more, many objects. So this is an image of a galaxy cluster. So each of these is an image. So if we put it through a spectrograph, so you see that the image gets split up into a longer chain. So this long chain is actually the spectra of the light. So this can tell us a lot about the constituent components of this image and the constituent components of the light, and hence the background stars and galaxies in that. And JWST has the capability of taking it along this axis, along the X and Y axis, which for astronomical reasons are necessary. The next camera is called NearSpec. So again, it's a near-infrared spectrograph. So again, it works from 0.6 to 5 microns. So both NearSpec and NearCam are NASA-based instruments, and NIRSIS is a Canada-based instrument. It's a imager cum spectrograph. So all of the JWST images near-infrared have infrared and imaging capabilities. But this has something very interesting called an IFU. So what is an IFU? I'm certain there might be only 1 or 2 people in the audience who know what an IFU is. And if they have forgotten what an IFU is, I'll office my mail. So IFU is called an integral field unit. So what happens is that if you take an image, so that's an image, right? So what you can do is you can break the image into several separate pixels. So here, for example, we have the image of Titan, which is the moon of Saturn, and you can break their image into several grids. So each of these grids can be used to actually image. So what can happen is now let's say if I want to take a spectra of this Titan. So what would happen is that I will put the slit and I'll be able to take a tiny narrow area of Saturn and get this spectra. But with an IFU, so what I can do is each of these grid points can give me a spectra. So you can have a very high resolution spectral image. So this image will tell us not just about the morphology of the object, but also what is the composition of that object at various different positions. So this is an example of a spectral cube. So for each of these points or pixels, we'll be able to get an individual spectra. So we can see that, for example, here, there are some lines which are missing in this particular region of this image. So we can get a 3D, it's basically called 3D because you have the XY image and also the third axis, which is the wavelength. So you get basically a wavelength plus images simultaneously. And this will be one of the most important instruments which is being flown on JWST. So it can not only tell us about the outer morphology, but also about how the gas is distributed, what is the elemental composition of the gas which we are looking at, or elemental composition of the object that we are looking at. So this will be one of the most important instruments that are being flown on JWST, that is the NearSpec imager. The fourth and the only mid-infrared instrument is called MIRI. So it works from 5 microns to 28 microns. So again, it's a spectrograph plus imager. So MIRI has to do all the work that was done with NearSpec, NearCam, and NIRSIS. So it's a single object spectrograph. It has an IFU. It can also do slit-lit spectroscopy. It also has a coronagraph, so you can block the light of the star and look at the planets. So this is the major near-infrared instrument, or the major workhorse instrument for JWST, and it will do a lot more interesting science. And with this, let's look at some of the science cases that the JWST has. So there are 4 instruments, 3 of them working in the near-infrared, which can do both imaging as well as spectroscopy. And then there is a 4th instrument which will be working in the mid-infrared, which can again do imaging as well as spectroscopy. So JWST has a variety of science cases, from exoplanets, which are basically planets around outside the solar system, to galaxies, to intergalactic medium, that is the medium between galaxies. It will also look at some of the solar system objects like the moons of Uranus, some of the other moons in the solar system, to Kuiper belt objects, Pluto. It will also look at the cosmological questions, like the question that was answered with the Hubble Deep Field Image, like what is the structure of the galaxies and structure of the cosmos at large scales. It will also look at stellar physics, So it will look at how stars are being formed. It will look at stellar clusters, so basically huge population of stars. And it will also look at supermassive black holes and AGNs, which are active galaxies, which are accreting matter onto themselves. So with JWST, we have, so each of this, somebody or the other has proposed for some projects that they want some X amount of time with JWST to observe something. So NASA actually came up with this document which tried to answer the 4 major questions. So let's look at the 4 major questions that JWST wants to answer. The first question that JWST wants to answer is the early universe. So as I told earlier that with Hubble, we were able to look at back to about 12 billion years after the 12 billion years, or about 1.5 billion years after the Big Bang. The first light that came out of the cosmos was only 400,000 years old, but we can't, so, and satellites such as COBE and WMAP were able to observe them. But at that point, when you're talking about 400,000 years old light, there are no stars or galaxies formed. So the first few million years after the Big Bang, nothing was there. And it's in the first few million years that the first stars started forming and the first galaxies started forming. So the first question that JWST wants to answer, or the big question that NASA wants to answer, is what were the first stars and galaxies like? Because we know nothing about these stars, and it's only when we look at very old light, very redshifted light close to the infrared, we'll be able to see them. So we'll be able to probe very close to something called the epoch of reionization, which we can discuss at a later stage, or if somebody is interested. So with JWST, we'll be able to go almost up to about maybe 13 billion years after the, maybe a billion years after the Big Bang, or maybe even less than that, maybe 500 million years. So we'll be probing the first generation of stars and the first generation of galaxies that would have been forming. The other JWST is science case is galaxies over time. So now that the first galaxies are formed, these galaxies were very different from the grand spiral galaxies that we see today. So most of the galaxies that we image, let's say even Andromeda, or the beautiful spiral arms that we see in pictures. So these are very relatively new galaxies. But the question is, how do these galaxies form? Because these are such a huge galaxies, and in the early universe, the matter density was not large enough to build such huge galaxies. So it is believed that these galaxies formed over several billion years. And most likely what would have happened would be that these galaxies actually cannibalized. By cannibalized, I mean they ate smaller and smaller galaxies until they grew. So basically it was like you eat smaller and smaller galaxies until you become a big galaxy. Even Milky Way has cannibalized many galaxies, and it's currently most likely cannibalizing one more galaxy. And we can see evidence for that in the Milky Way. And JWST will actually look at some of those evidences as well. And so it is believed that galaxies evolve over time. And the question is, what role does dark matter and dark energy play in that? So over the 13.5 billion years, the contributions, what was the contribution of dark matter and dark energy in developing the galaxy structure? And you can clearly see, for example, so these are some of the oldest galaxies that Hubble has seen. So clearly you can see that these are not the nice grand spiral galaxies that we typically associate with Hubble images. These are irregular galaxies. These are basically blobs and clumps which we see. And these are at very old redshifts. So these are very old galaxies. But if you look at some of the nearby galaxies, we can see that there are many beautiful spiral arm kind of galaxies here. But you can also see that these galaxies, most of them are also interacting with each other. For example, if you look at this galaxy, it looks like two galaxies are passing through each other. Some of the galaxies are colliding, some of them are merging, some of them have merged. So we see that there is a lot of, with Hubble, we were able to detect a lot of galactic interactions and also image very irregular first galaxies. So this tells us that significant amount of evolution in the galaxies has to happen to give us these grand spirals that we associate with. Even with the Milky Way, we associate. So this was the second big question that JWST wants to answer. The third big question, which is also very close to my heart, is how stars form. So star formation happens in dense interstellar environments. So one of the famous images that Hubble gave us was this. This is the Eagle Nebula. It's called the Pillars of Creation. And you can see that there's a bright light coming from the background, but you can see that there is mostly this red brownish dust, which is blocking most of the light. And yeah, it's actually dust. It is the same dust that we find on the Earth's surface. We find in our houses. We find on our clothes if we leave them out for long. So this is the same dust. And this blocks most of the light in the optical wavelength. So if you observe them with infrared instruments such as NIRSpec, NIRCam, and even with JWST, even with Hubble, we were able to get some infrared images of these objects. So you can clearly see that behind these pillars of dust or pillars of creation, there are small stars. So stars are actually embedded in them. So some of them you can see as very faint stars, but once you look at them in the infrared, they just bright up. So you can see a lot more stars in the infrared because these are being blocked by the light, or because of they are being blocked by the dust. So near infrared and mid infrared observation of clouds where star formation is happening is very important to understand the star formation process. And this can also lead us to and provide us with important clues about the planetary formation processes as well. And we at TIFR, at least my group, has been working on this aspect for quite some time now. And the third and the fourth and the final aspect of JWST was exoplanets. So there is a very interesting meme or very interesting line of thought that goes, if you're working on exoplanet, so any telescope that NASA launches, any telescope that anybody launches or builds, exoplanet researchers will come like, our telescope. So they're like very secular and very communist in this manner. Whatever you build exoplanet, people will find some way of using it. So even JWST, when JWST was first thought of, there was only one planet detection. But now a major time of JWST will be devoted towards detecting exoplanets. So what will JWST do? So this is the fourth pillar of JWST, is looking at exoplanet science. The main question that we have been trying to answer with JWST on the case of exoplanets would be to detect oxygen and other biomolecules in the atmospheres of Earth-like exoplanets. So we are basically hunting for clues for life. And since we don't have any good idea about how extraterrestrial life should be like, we are assuming that it will be like Earth-like, and it will take oxygen, it will produce methane, it will need water. So we are assuming that it will be very similar to what we have on Earth. So we are looking for signatures of biomarkers like oxygen and water in the atmosphere. Of water and oxygen atmosphere, oxygen observations from Earth are difficult because our atmosphere actually has water and oxygen in it. So we actually get absorption features in the spectra that if you observe from Earth. So it's very difficult to rule out whether this is coming from the exoplanet or whether it's because of our own atmosphere. So because of this, we need to go into space where there is no atmosphere. So we can actually look at the signatures of biomolecules and these biomarkers very carefully. And I was also saying that there are also chronographs being installed on JWST, which can block the light from the central star. And because of this, we'll be able to detect and image smaller and smaller planets around them. So these are the main questions about JWST. So now let's look at when was JWST launched. So when I joined my PhD in 2015, my PhD supervisor was like, Mayank, JWST is launching the next year. You'll work on JWST data. Okay, my first year happens, second, third, fourth, fifth, sixth. And now you're like, Mayank, JWST is just going to be launched. Just wait 2-3 months. And finally it launched. So there was a huge meme going on that there is a planned launch date, which is shown in red. And there's a dotted current date. And eventually people thought that eventually the planned launch date and these will merge and it will launch somewhere in 2026. But at least that didn't happen. Then it was decided it will be launched on 18th of December. And what do we say about JWST launch? Not today. So we're like, okay, take one more day. Then it was 24th of December. I'm like, aaj to pakka launch. It will definitely launch today. This is going to be a Christmas present. Nothing happened. Then it was 25th of December. And then I was hoping this will happen, most likely. The launch will be like T-minus 9, 10, 9, 8, and then there will be like, ho, Santa Claus will come and then we have to stop the launch. But thankfully, the launch happened on Christmas Day 2021. So it was launched from French Guiana. So this is it's in South America, but that area is still controlled by France. So it was launched on board an Ariane 5 rocket from ESA. So here I'm showing some clips from that. So the launch was spectacular. Like because of clouds, we could not see beyond the first 30 seconds. But we actually got a first image of the telescope in space. So this was the first image. And this was like when the telescope finally opened up its solar panel. So it's being powered by solar panel. So this was like a huge sigh of relief because interestingly, JWST had something called single points of failure. So a single point of failure, as the name suggests, if this goes bad, the telescope finishes. It's over, khatam. So it had 343 of such points. So this was the first single point failure. So everybody was like, okay, 1 out of 343 done. And then over the next 10 days, it was like 10 out of 343 done. So let's look at how the JWST telescope was commissioned. So this is like the timeline. So I'm sorry, this is slightly smaller, but it was launched from Earth. Then the solar panel arrays were deployed. Then what happened was the signal, high gain signal antenna was deployed, and then the telescope started unfolding. So let's look at how the telescope. And before that, some of the very keen astronomers on Earth, they were able to actually image JWST from Earth. So this tiny dot you see going through the scuttling through the field of view of stars, you can see, right? So I'm pointing it here. So this is actually JWST telescope. Somebody actually went out, tried to observe. And interestingly, there were some people from IAA, that is the Indian Institute of Astronomy and Astrophysics. One of the telescope operators were actually able to take one of the photographs from Bangalore, close to Bangalore. Unfortunately, I was not able to find that photograph, but if I find it, I'll post it on the ChaiNY page. But yeah, so people were very excited about this telescope, but still we were like, okay, there are many more things that can go wrong. So this is how the JWST telescope will unfold. So this is the sun shield, which would eventually unfold and puff up to protect the telescope from the heat. Then the two mirror segments will also open up, revealing the complete telescope. And so this is how it was thought and planned it will launch. So people were like, whether this will happen or not, nobody knew. But thankfully, everything went very smoothly. Like each day, I would stop the JWST Instagram page like, this happened. Very good. Okay, one more thing done. So with this, we were able to actually finally commission the JWST telescope. And JWST, whoever is controlling the PR team has a very nice sense of humor. So when JWST launched, there's a question, yeah.
Those images you said you showed of not the simulations.
This one.
Not the one before that where you could see the solar panel being deployed.
I'll get it.
How was this one? Yeah. How were these images taken?
Oh, because the Ariane space rocket that the question is how was this image, or even the image in the previous one, this image taken? So the Ariane space rocket, the rocket capsule actually had a small camera on it, so which was basically pointing towards the telescope just to make sure that everything is happening okay. So this was taken from the once the telescope was basically ejected from the satellite or the launch vehicle, there was a camera on the launch vehicle which was positioned such that it could image the telescope and image this solar panel deployment happening. So that is how it was imaged. Yeah. So there was a camera on the launching vehicle itself that put up there. So yeah, as I was saying that the NASA, whoever is controlling the JWST Twitter handle has a very nice sense of humor. So after the sunshade was deployed, so there was a tweet from JWST. So that NASA at the rate sun, NASA at the rate moon, NASA at the rate earth, all of them were blocked, as in the sun shield was deployed and all the sun, earth, moon light coming from them were blocked. And also JWST blocked the Twitter handles, which I found to be very hilarious. And thanks to Arnav for sharing that meme with me. So JWST has a very interesting science community. As I was saying, it's going to be put in L2. So this is going to be, this was like again a 30-day, it was called the 28 days of terror. So it almost took 28 days for JWST to be launched and to be put into orbit. And like each day we were like, okay, now the sun shields have been deployed. The telescope has started cooling. And then there was an insertion burn at around I think on the 26th or maybe 24th, on the 23rd or 24th, where the JWST was finally put into orbit around L2. So the JWST will not actually be at L2. So if you can look at this image or this slideshow, you can see that the telescope will be orbiting this point called L2 and it will not be at L2. There are very complex reasons why it's not going to be at L2 but orbit L2. And if anybody has those questions, we can discuss them later at a much.
While you're on this slide, while you're on this slide and this video is playing, maybe I see a lot of questions in the online thing that people don't realize that the L2 point is also moving. The Earth
okay, yeah,
around the
So this is
to the Earth sun.
Yeah. So this is a question from the chat that it's a very good fine observation from the people in the observing as well. So you can clearly see that this L2 point is also moving because let's assume that the sun is fixed at the center. Because the Earth is moving around the sun, the gravitational force between the Earth sun JWST system will also move because it's again the gravitational force of the Earth is moving. So what will happen is that the stable point that is L2, that stable point will also move, but it will move such that in relation to Earth and the sun, that from an observer, On L2, it will look like it's always been staring at the same point.
So
Yep.
now
Hmm.
the question is, doesn't the moon go around the Earth, and hence doesn't your L2 point change?
So again, so there will. So the question is, since the moon also goes around Earth, will that change the L2 point? In principle, it does. The L2 point will shift, but because it's a gravitational interaction, and we physicists are at some point very lazy. So what we do is because the Earth Sun system is much more massive than the Earth Moon system, we'll just neglect that term. We'll say that there are going to be some corrections. There are also going to be corrections from not just the moon orbiting the Earth, but also remember, it's just not the Earth, Moon, and the Sun. There are also other 7 planets around as well. So all of them will actually have some perturbations or some pushing and pulling on the orbit. And one of the reasons why the JWST will orbit L2 and not be at L2 is because of this pushing and pulling. So it becomes very difficult to have a stable planet or a satellite at that orbit. So JWST will need to do course corrections. So every 21 days, JWST will fire a small rocket, like small. So JWST has many small rockets in it. So it will fire it for some time so that it can correct its position. So these are called course correction maneuvers. So JWST after every 21 days will have such maneuvers. Because of this, because of the interaction between the planets, the moon, Earth Moon system. So because of all of those interactions, they're going to be maneuvering.
And how far is L2? Is it like 1 million kilometers? Like
Yeah.
some idea of how far
Yes.
is L2?
So how far is L2 is another good question. So the moon is like 300,000 kilometers away. L2 is going to be 4 to 5 times much farther away. So we're talking about 1.5 million or 15 lakh kilometers away from the Earth. So it's a very far away orbit, and that is why it took almost 30 days to reach that place. Any other questions from the chat window? Okay.
No, there are many, but we'll take them later.
Okay. So with this, basically, I'll try to end this talk with the so this is how we expect images from JWST, even if at the best of times we'll get images which will look like something like this. These are like snowflake patterns. So if you really look at a bright object with JWST, we'll have such snowflake like kind of patterns. But since with JWST, we won't be looking at very bright objects, we'll only be seeing most likely the central area. But this to me looks very beautiful at some point. And if I would be there, I would at least observe 1 or 2 bright objects to see how this looks. But yeah, with this, I'll mostly end my talk. And if you want to talk about my work with JWST, we can discuss this later. But there are 2 JWST projects that I'm involved with. One is called Investigating Protostellar Accretion Across Mass Spectrum, IPA. IPA, as everybody knows what IPA stands for. It's being led by Professor Tom Megath from the University of Toledo. So we have been given 65 hours to observe 5 protostars. So protostars are basically the earliest or the first stages of the star and planet formation process. So these are very deeply embedded objects, and we'll be looking at them using the instrument MIRI and NearInfrared. So MIRI, MRS means medium resolution spectroscopy, and NearInfrared IFU means near infrared spectrograph with the integral field unit. So this would be one of the first projects that I'll be working with JWST. The other project that we are involved with is called Illuminating the Dust Properties in the Diffuse ISM with JWST. So this is being led by Sasa Jigar from Asia A. It's a 31-hour project where we'll be looking at the mineralogy of dust in the ISM. So we'll be looking at how dust is formed. So the dust we see every day on our Earth, how that kind of dust is formed. How does that dust evolve with time? So we'll be looking at such questions, which can then be which are very important, because most of the rocky planets that we see on Earth and in the universe, they are made of iron, silicates, aluminium, magnesium, and we want to see how these materials in dust evolve with time. So with this, I'll actually end my talk, and if you have any questions, we can answer them.
Okay, great. So I'm sure the online audience has a lot of questions. I think this camera is picking up my voice, certainly. There are a few interesting questions online. We'll take them first, and we'll take a quick break after that. So the first question is, is JWST going to be used mainly for deep field imaging, or also are we going to look at stuff nearby?
Yeah. So as I was saying that the JWST though has 4 pillars that it wants to answer. There, if you look at the list of accepted proposals, I'll go to that slide. 1 second. Yeah. So these are the science questions that JWST answer. So it will be looking at both the very deep early cosmology, but it will also be looking at even objects much closer in, basically looking at solar system objects. So looking at moons of Jupiter, Saturn, Uranus. So moons of Uranus is a huge target for JWST.
Okay, now there is a question which is not really a science question, but it's such a nice question, and somehow I think everybody has had this question. Okay, Khwaish is asking if every other planet's moons have names like Titan and whatever and whatever, Ganymede and something else, and moon is a generic thing for something that goes around a planet, why doesn't Earth's moon have a name?
So this is like a long-standing controversy. There are Earth's moon at some point is also called Luna, but there are some controversies regarding that. So
okay. Yeah, you have the answer? Yes, go ahead.
Go ahead.
Because Earth's moon is found first.
Okay, so first moon, and hence the moon is the first moon. Okay, lovely. Thank you. Okay. Is the JWST looking at what kind of galaxies were common in different points in time in the universe, in different epochs?
That's an excellent question, and that is one of the science goals that JWST has, is to look at what kind of galaxies were present at the early universe and how those galaxies evolved to form the grand spiral galaxies that we see today.
Okay, a question right from the very beginning, which I have been saving. You showed this Hubble dark field picture.
Deep field, yeah.
Deep field. There is the top right has a dark patch.
Yeah. Oh, that is because that is how the CCD array was tagged. So this is basically an artifact of the CCD array. So any Hubble image that you look at from that era, it will have that L-shaped kind of a geometry.
Okay. Does every two-body system, Dhruv is asking, have 5 Lagrange points?
In principle, yes.
Okay, let's stop it there because it's going to get complex. Okay, Prasad, Uma, a lot of people have asked, if L4 and L5 points are even higher stability, why don't we send telescopes there or objects there?
Yeah. So first of all, L4 and L5 are much farther away. And the thing is, at some point, we want to block the glare from the Earth, right? Or the glare from the sun. So by placing an object at L2, we'll actually be stopping both the glare from the Earth-Sun system, as well as I was saying, that the telescope needs to be close enough that we can still be in constant communication with it. So placing the telescope at L2 will make sure that we have constant communication with the telescope as well.
Okay. And I think Priyanka is a young student who's been asking fantastic questions. You said there was interstellar, whatever, dust and all that stuff.
Yes.
What if it sticks to the mirror of the JWST?
That's a good question. So close to the Earth-Sun system, we don't have much of this dust. There is something called the zodiacal dust, but that is again in a very special orbit, which the JWST will be avoiding.
Okay, and this looked like it was going in an orbit around
L2.
Around L2.
Yes.
How big is that orbit?
So that orbit is going to be something like I think it's about 200,000 kilometers. So that's about basically the orbit of the, slightly larger than the orbit of the moon. So it will also be changing its shape. So
okay. And I think where there are tons and tons of questions, but we need to also give people that it's 12:30 here. Yeah. Who is James Webb?
Oh, James Webb.
You haven't told us anything about James Webb.
Okay.
And why is the telescope named after him?
That was something which I've been avoiding. It's also a slightly controversial issue as well. So people tend to call it also the Webb telescope. So James Webb was a NASA administrator during the Apollo era, and he helped basically put the first man on the moon. Why it's called James is because they wanted to honor him, and there are certain controversies regarding that his career and his legacy. So that's why I avoided talking about that.
Okay. In fact, there was a whole thing about change the name of the telescope.
Yes, there was a huge campaign
to NASA. But
yeah.
Anyway, okay. Do we have to worry about solar storms?
With JWST, like with any satellite, there is always going to be some amount of solar. There's going to be some threat from solar storms, but it's at a very far away distance. And one of the reasons why this thing has kept on is because it's also a very good conductor. So even if there is a charge buildup at one of the sides because of a solar storm, it can actually be neutralized. So
also you are in the shadow of the Earth in that case.
yeah. But again,
Not much.
those are current. Yeah. Okay.
Okay, I think that's good. If you have more questions, please post them, email them to outreach@TIFR, and we'll try and take them. So at this moment, I want to thank the online audience. You guys have been fantastic. We've got more than 100 questions. I tried to answer most of them, many of them. We couldn't take all of them, but please write. I've given you links and also something, so don't worry. And our next one at Prithvi will be on relativity and the ultimate speed limit. Before that, we will have online Chai in mid-February. We'll let you know the details. Follow us. outreach@tifr.res.in is our email address, or follow Chai on Twitter or Facebook. We will let you know the details. So with this, we will end the live stream right now. The best part about attending in person is you get chai at Chai and What is Chai without chai? So I invite all of you here to a cup of chai outside, and we'll come back and we continue the discussions. The live audience, thank you so much. Thanks for watching, and keep tuning in later.
Okay. So I should leave this. So you'll end it.